Section 5.6, exponential functions as models. We're going to be working with a model today that should look very familiar to you from what you did in college algebra, hopefully, or algebra 2. It's the exponential growth and decay model. It looks like this. Now, when you saw in algebra 2, the variables might have been different. This text is the first time I've seen it with Q, but you might have seen it with Q before. Either way, you've got this quantity Q and you're measuring it at some time T, and it's dependent on the initial value of Q. So we're going to see this Q sub naught, it's little Q sub 0. This is the initial quantity. I'll just be calling it Q sub naught. And then you're multiplying that by e to the kt. Now, T is measured in time. You'll be given some sort of unit for that, but K is the growth or decay constant. So if K is positive, then you're looking at a situation where you have exponential growth. And if K is negative, you're looking at exponential decay. Now, that's a constant value. Notice how many variables you have in this function. That means that a lot of what you're going to be doing in these problems is you're going to be setting up the function for exponential growth and decay, and you're going to be using some given information to solve for your growth constant K. Once you have that, then you can rewrite your growth or decay model and use it to answer another question. So for a lot of the problems that we're going to be doing here, you're not just like answering one question done. Usually you have to complete part of the model first by finding the growth or decay constant K, and then you're using that model to answer a question. Like I said, hopefully you've done this before, but if you have not, I don't know, it's not like a crazy thing. It takes a little bit of algebra and know-how, but I think you'll be just fine in this section. So let's get going on it. A culture of bacteria initially contains 2,000 bacteria. So if we're given an initial quantity, that's one word we really want to pay attention to. Initially contains 2,000 bacteria. We're going to let that be Q sub naught, because remember that Q sub naught is representing the initial quantity. So the 2,000 is going to be our Q sub naught. After 2 hours, it has 18,000 bacteria. Find a function that models the exponential growth of the bacteria after 2 hours. So the first part of this, we're just finding a function. So don't feel like, oh my gosh, I need to find an answer here. We're just writing the function for part A. So what we're going to do is use the fact that Q sub naught is 2,000, and we're also going to use the fact that when T is 2 hours, Q sub T, our quantity, is 18,000. So what this means is Q of 2. So this is bringing us back here. Q of 2, when T is 2, is 18,000. So we're going to be using these two together in order to get this model for what happens after T hours. So let's go ahead. In order to do this, if I know that Q of 2 is 18,000, I'm going to rewrite this down here. I know we just have it just directly above us in that box, but I want to be able to write this down and put in the components underneath. I know that Q of 2 is 18,000. Sorry, I don't know, my internet's like, it keeps flaking on me. Okay, I don't know, hopefully it will, I don't know what to say, you guys. All right, so I'm gonna be letting T be 2, and then Q of T is 18,000. So the initial amount of the bacteria, Q sub naught, is what I'm going to fill in next to the right of the equal sign, and that's 2,000. And then I have E, which remember is just a constant value here for the base, and then to the K. And now T in this case, we're going to let be 2 because I'm using Q of 2 to get to 18. So I'm using some given information to write a model. That's all this information is doing. We're not doing anything else with this except just getting the model put together. All right, let me get my calculator out. We are definitely going to be needing our calculators today. One thing you probably don't need it for, though, is solving for K. So the first thing we're going to do now that we have all these components together is notice that you just have one variable left to find. In order to solve for this variable, you want to isolate this exponential expression. So we're going to divide both sides by 2,000. When I do that on both sides, the 2,000s will cancel. And then I've got 18 divided by 2, which is 9. So 9 is e to the 2k. And I'm going to be really, really particular here about leaving the value of k exact. I don't want to round it off because I'm going to be using it again in part B and part C. So I want to leave it exact. I know it's cumbersome, but it will allow you to make sure that your final answer is the exact final answer. So if I'm trying to solve for k, I want to get k out of the exponent. To do that, I'm going to apply a natural log on both sides of the equation. And remember that the natural log of e to the 2k is just 2k. So now I have the natural log of 9 is equal to 2k. And then to get k by itself, by 2. And it looks like that. Now, remember that what I was actually asked to do in this problem was find a function that models the exponential growth of the bacteria. I just found the value of k that we need for the function. So what I'm going to do now is I'm going to go back to the original function that I found. Everything is going to stay the same, except I'm going to plug in the value for k that we found, and I can go ahead and plug in the initial value because that's not going to change. We were already told the initial value was 2,000. That's 2,000 all the time. What's going to change is, the amount of hours and the amount of bacteria after a certain number of hours. So I want to keep q of t and t variable. So we can go ahead and rewrite this as q of t equals 2,000 e to the ln 9 over 2 t. And you're going to have to try to be careful here because I know there's a lot that goes on in this exponent, and we want to make sure it still looks like it's in the exponent and it's not just getting multiplied by the function. So the ln 9 over 2 times t is all in the exponent here for this function. Now, we use some given information to find a model that represents the data for this exponential growth. And if you're not sure, well, like, how would I know if it's growth and not decay? Well, remember that we're looking at a value of k that's positive in this case. If you're not sure, take your ln 9 and divide it by 2, and you do indeed get a positive value. But it's also bacteria. You know, the bacteria is just going to multiply. All right. So that's the function. There was one more thing I was going to say about this function, but I can't remember what it was. Make sure to leave this k exact. Okay. I don't know what else I was going to say about it. All right. Part B, how many bacteria are there in 4 hours? Well, 4 hours represents the value for t. So we are going to find q of t. So find q of t when t equals 4. In order to do that, I'm looking for q of 4. So you don't need to do anything else at this point except use the model that you already found whenever t is 4. So this will be 2,000 e to the ln 9 over 2, and you're going to multiply that by 4. All right, so this is all going to get put in our calculators, and we're going to make sure that we're doing a very good job here with our parentheses and making sure everything is where it's supposed to be. Oh, you know what? I just remembered what I was going to say earlier, but can't remember exactly the way that a student phrased this question in the past. So you know what? I'm going to think a little bit more about what the question is exactly. I'll get back to it. Okay. 2,000 times e to the ln 9 over 2. So ln 9, don't forget to close that parenthesis, divided by 2 times 4. your calculator knows to take the natural log of 9 and divide by 2 and multiply by 4. Even if it knows to multiply by 4, then divide by 2, it's the same thing. So it'll know what to do. Just make sure everything is still staying in the exponent. And when you do that, you get a value of 162,000. Now, notice that you only got such a nice value because you did not round off your value of k. If you had entered k as some sort of decimal approximation of ln9 over 2, you would have gotten something close, but it wouldn't be exact. Let me show you. ln9 divided by 2 is approximately 1.0986. So let's say that instead of using the exact value, you were like, we'll just truncate it out. We'll use 1.099, and we'll just multiply that by 4. Well, you get close, but you're off in this case by 251 bacteria. Another bacteria. I know when it comes to bacteria, 251 of them isn't that big of a deal, but might be a very big deal to you if you're a scientist. So make sure you're using an exact value of k. Notice how you're, even just by rounding it off just a little bit, how far you're off from the actual value of the number. All right, so I'm going to put this value down here as 162,000 bacteria. We do still want to label our answers. How long means find t, find an amount of time until there are 1 million bacteria. So we're going to say find t when q of t is 1 million. So we're going to do that now. So I'm going to set our q of t to be equal to 1 million. Again, I'm using this initial function that we found in part A. So we're going to set q of t to be equal to 1 million. You don't have to include the comma if you don't want. Sometimes they throw people off, but you don't want to lose track of how many zeros you have. So I include them for that reason. All right, so this is going to be equal to 2,000 e to the ln 9 over 2 t. So how long until there are 1 million bacteria? So now we just need to solve for t. To do that, divide both sides by 2,000. I'm going to show this so you can see it. Okay, when you divide by 2,000, the 2,000s go, 3 of those zeros go, and then you have 1,000 divided by 2, which is 500. Am I still on the page? Getting close. So 500 is e to the ln 9 over 2 t. And I want to make sure this is not ln 9 halves. So ln 9 over 2. Should keep parentheses on that. All right, now I'll just solve for t by taking the natural log on both sides. So this sort of takes us back to what we were doing when we found k in part A. This time we're just solving for t instead. So let's go ahead and take the natural log on both sides. We'll say ln of 500 is ln of e to the ln 9 over 2t. Now, if you feel like, okay, we already know we're doing ln on both sides and e is already by itself, like, do I have to write ln e again? No. If you wanted to just say ln 500 equals and then just bring your exponent down, that's fine. You're going to get used to doing this. I'm just, these are initial problems that we're working on here, so I'm showing every single step. I'll probably start skipping that step here pretty soon. So our exponent is ln 9 over 2t. So if I want to get t by itself, in that case, I'm going to say that t equals ln 500. I'm going to divide both sides by ln 9 over 2. Okay, and we're gonna have to be careful with how we put this into our calculators. We could just remove the complex fraction here, but I don't want to make this look super complicated. So we'll just solve for a value of t here in our calculators. Simplify this value out a little bit. So this is going to be, maybe I should make it brighter. All right, ln 500 divided by, and then I'll just put this whole thing in the denominator, ln 9, close the parenthesis, divided by 2, close your denominator. And you should have about 5.657. Let's use 2 decimal places, and we'll just say 5.66. Now, I think sometimes when we're dealing with time, students tend to just pop years on there. I don't know why. We're used to seeing years as a unit. So students are like 5.66 years next. It's not years. We're talking about bacteria. How long until there are 1 million bacteria? Well, look back to your original problem. This was talking about growth in hours. So we can go ahead and make the assumption that when we're talking about hours and hours, this would make sense if this was in hours also. I mean, if in 4 hours you have 162,000, there's no way it would take 5.6 years to get to 1 million. So you can go ahead and make that assumption that we're talking about hours here, since that's the unit you were given. All right, so just lots of algebra work here with these exponential and log expressions or equations, if you will. All right, let's do another one. Radium decays exponentially. Oh, it decays. So we're expecting our value of K to be negative in this case. It has a half-life of 1,600 years. So what that means is that after 1,600 years, the amount of radium that you have left is half of the original amount. So if there's initially 50 grams, find how much is left after 400 years. So if the half-life is 1,600 years, that means that after 1,600 years, we have half of 50, which is 25 grams. So we're going to use this information to put together an exponential model that will help us to display this data, these quantities. Okay, so we can go ahead and say that Q of 1,600, so this is using this idea of the half-life, is half of the original amount, which is 25. So we know that Q of 1,600 is 25 grams, and we originally have 50 grams. So we don't know any information right now, however, about K, which is the decay constant. So remember how I said a lot of times the first thing we're going to have to do is find K. We don't have it, we're going to have to find it. So I initially have 50 grams, and this will represent Q sub naught. Find how much is left after 400 years. Well, that's going to represent T, but first we need to focus on finding that K value that represents that that decay constant. So first find K. All right, so in order to find K, I'm going to plug in the information that I do know. So I do know that my amount is 25 when the time, when T is 1,600. So I'm going to plug this in and I'm going to say, okay, I know my amount is 25. The original amount, Q sub naught, is 50. And then E to the KT. In this case, I'm going to go TK because I know T and I just like to have the coefficient in front of the variable. But that is up to you. So we have 25 equals 50 times E to the 1,600 K. And then we'll solve to find K. So our initial amount, final amount after 1600, all that's in this equation right now, or this function. Go ahead and divide both sides by 50. Now, 25 divided by 50 is a half. Well, that's going to work out nicely for you in all of these half-life problems. So even though, yes, technically we put it together like this, you can always say for half-life that 1/2 is e to whatever the half-life is in years. Okay. So 1/2 is e to the 1600k. And then again, when we're trying to get k out of the exponent to solve for k, all we need to do is take the natural log on both sides. So the natural log of 1/2 is equal to 1600k. And then divide both sides by 1600. And that's the value of k. Now, there's a lot going on here. So one thing I did want to note to you is that you might see in your book that ln 1/2 is rewritten. But we know that ln 1/2 can be rewritten as the ln of 1 minus the ln of 2 just by using that quotient rule for logarithms. The natural log of 1, though, is 0. So this just ends up being negative ln 2. So if you see negative ln 2 instead of ln 1/2, don't panic. It's just because they rewrote it, and a lot of times we just simplify out something like the natural log of 1 being 0. So this would be equivalent to saying negative ln 2 over 1600. And this is a decaying quantity because ln 2 over 1600 is a positive quantity. I know it's negative, 10 to a negative exponent. So it's a very, very small quantity. But when you put that negative sign in front of it, you can see that k is negative. Therefore, we definitely have this decaying quantity. We found that k was negative. All right, once you find k, go ahead and plug that into your function to answer the question. So this would be the second part. How much is left? So find the quantity after 400 years. So I'm going to say next, find Q of 400. So we're going to let T be 400 in this case. And at this time, we are talking about time in years. Okay, so now I can go ahead and write the function. I know that Q of, I'll just go ahead and rewrite the whole thing. Q of T is the initial amount times E to the negative ln 2 over 1600. I know it's so much T, but leave it exact. Your reward will be at the end when your answer is exact and you're not trying to enter all these bizarre decimals into WebAssign. Run your test when I say leave your answer exact. Approximate at the end. There's a place for that. All right, so Q of 400 is 50 times E to the negative ln 2 over 1600 times 400. Okay, so let's go ahead and plug this into our calculators. Once everything is exact, you can approximate your final answer. So just go ahead and enter this whole thing into your calculator. So this is going to be 50 times e to the, be very careful with how you enter this, negative ln 2, close the parenthesis, divided by 1600 times 400. And you should get 42.04-ish. And that's grams. Looking back at your question, it'll tell you what your unit should be. And that is the answer to part A. So first you found K, and then you could actually start working on part A. So that's the thing. You can't actually answer the question until you find the model, and you need K to get the complete model. So a lot of these, like I said, are two-parters. How fast is the radium decaying after 400 years? So you were asked how much was left after 400 years, but now you're being asked how fast is the radium decaying at 400 years? The decay is a change in a quantity. How fast is the quantity changing? Can you guess what you might need here? It's a rate of change of the quantity. It's a derivative. So we're going to need to find the derivative. So if you were thinking like, oh, this is all just algebra, no big deal, I'm going to get through this section without using any calculus at all. I'm sorry, there is some calculus. Not as much as I had hoped, but there's definitely some calc in here for you to do. So have no fear. We're going to do it right now. All right, if we're going to find the derivative of Q and then evaluate it at 400, I first need to rewrite my function for Q just as a general Q of T. I can't take the derivative of this because this is just a constant value. It's only going to tell me it's 0, and then we're going to be confused. But make sure you're taking the derivative of Q of T. I'm going to write it here to remind you of what that looks like. It's e to the negative ln2 divided by 1600 t. Now, when we take this derivative, the only thing we really need to worry about here is taking the derivative of the exponential function. We don't need the product rule, and that's because 50 is a constant multiple. There's no variable in the base of 50 here, or in this factor of 50. But we will need to apply that exponent rule for derivatives for exponential functions just by chaining out the derivative of the inside function. The inside function here, since maybe it's been a few days since you've done these, is negative ln2 over 1600 t. Its derivative is just the multiple, the constant multiple that's in front of it. So I know it looks weird just because there's so much going on, but this is just the constant. So we would say the derivative on the inside is just this constant value, just like how the derivative of 2t would be 2. Same idea. There's just a little more going on here. All right, so let's go ahead and take q prime. Q prime, we're going to just keep that constant multiple in front. And then we have e to the negative ln2 over 1600 t. And then we're going to multiply the whole thing, not the exponent, the whole thing, by the derivative of the inside function, which is negative ln2 divided by 1600. Now, if you would like to go through and simplify this, you can. And you could, I guess, simplify between the 50 and the 1600. But honestly, you're just being asked here to determine how fast the quantity is decaying at a certain point in time. You're not being asked to find a derivative and simplify it. So if I were you, I would just use this derivative to evaluate the rate of change at 400. I wouldn't bother simplifying it at all. I know it doesn't sound like me, does it? Negative ln2 divided by 1600. That whole quantity is getting multiplied by 400. So that quantity we already have in our calculator. We're just going to take that and multiply it by negative ln2 over 1600. So notice this quantity right now is exactly the same as what we had before. We're just multiplying it by negative ln2 over 1600. So what that is going to look like is, let's see, this was our answer from before. I'm going to multiply that by, don't forget your parentheses, negative ln2, close your parenthesis, divided by 1600, close your parenthesis, and we get negative 0.0182. Let's write that down because we're going to have to put a unit on that. Negative 0.0182. Put the 2 on there. Okay, so we're being asked how fast is the radium decaying? Well, this is measured in grams over per unit time in years. We would say grams per year. So it is decaying, but by a very small amount. So it's negative because the value is going down, but it's going down very slowly. We're talking about things that are happening over the course like hundreds and thousands of years. It takes a long time for that decay to occur. Okay. Now we'll talk a little bit about carbon dating. For problems involving carbon dating, carbon-14 has a half-life of 5,770 years. You'd like to see that box, wouldn't you? I mean, it is on your notes. But all right. So let's go ahead and work on one of these carbon problems. We're going to find the decay constant K in a carbon-14 exponential decay model. So in order to do that, we're going to use the half-life, just like we did in the previous example. So last time we looked at a half-life of 1,600 years. We found K, and we were like, okay, we know the final, we know the initial, so let's solve for K. This time, it's a little different because last time we were given this value of 1,600. This time, we technically weren't given that value in the problem, but you're being told this value. If you're working on your homework and it's talking about carbon-14 and it doesn't give you this value, it's probably because they assume you have it somewhere in your notes, but just make sure you have this. I mean, here, I'll call it out in case you need it on your homework and it's like not there. If it's like the half-life of carbon-14 and you're like, I don't remember where that is, it's right here. So. All right, so let's use that. But a big difference between this problem and the last one is you are not given an initial quantity. So you're given a half-life, but last time you were told like, okay, we initially have 50 grams, and now you're just like, okay, you gave me nothing but a half-life. Okay, but we can still use that. So if we know, for instance, that we have this exponential model, I know that it looks like this. I know that T in this case is going to be 5770. I don't know the final and the initial amounts, but it doesn't matter because I know that the final amount is going to be 1/2 of the initial amount. So if I wanted to write this, I could say that, let's see, I'm going to write this in words. Final amount is 1/2 initial amount in 5770 years. So we can use that in order to solve K and get our constant. Okay. So I know that the final amount is 1/2 the initial amount, so I can rewrite my Q of T to be 1/2 of the initial amount. Is the initial amount E, the KT. The final amount would be our Q of T is 1/2 the initial amount. That's where this comes from. And then put this over here. All right, so now that we have that, well, we have Q sub naught on both sides. You can divide both sides by Q sub naught. When you do that, they're both going to divide out. Q sub naught divided by itself is just 1. So that means you have 1/2 equals E to the KT. And this will work for any half-life problem. Technically, it worked for the first one we did. It just, you couldn't tell when it happened. You had ln 1/2, or I'm sorry, 1/2 was E to the half-life K. And then now we're going to do the same thing. 1/2 is E to the half-life K. I should have plugged that in for T, sorry. We'll do that now. 1/2 is E to the K times 5770. And then we'll solve for K. So take the natural log on both sides. So now we have natural log 1/2 is 5770K. And divide both sides by 5770 to get K. And remember, ln 1/2 you can rewrite as negative ln 2, should you so desire. Sometimes just having a fraction and a fraction just looks more complicated. So you can always do that. So this is the decay constant, K. That's all we're asked to find here. I have a note here that I want to give you. Note that for any half-life problem, we can say that K is ln 1/2 over the half-life. Okay, so that works here. Or you could say it's negative ln 2 over the half-life if you like that better. You decide. So you can always use that as you're working through your homework if you'd like, although I do think it's good to see where it comes from. All right, so now let's answer a question based off of the carbon-14 dating, which hopefully you've heard of before. A skull is found and it has lost 31% of the original amount of carbon-14. How old is it? First of all, I'm going to rewrite this constant K that we just found up here, just so that we have it. We said that K was equal to negative ln 2 divided by 5770. And that's from problem 4. Okay, so we have that. And that's specific to carbon-14. So that's what we found in problem 4. A skull is found and it's lost 31% of its original amount of carbon-14. How old is it? So what we're trying to find out is after how many years was this skull found? Now, if it's lost 31% of the original amount of carbon-14, what that means is it still has 69% of the carbon-14 left in it. So we can do is we can set up a similar type of function that we did when we were finding half-life, but instead of thinking about this in terms of half, we can think about it as the 69% that we have left. So let's go ahead and formalize this into a function. We can say, if we think of 31% as a decimal, 1 minus 0.31 equals 0.69 remaining. Okay, so it lost the 31%, so it still has the 69% left from the original. So whatever the original amount was, we don't know. So let's go back to our original model and we'll fill in the pieces that we can find. So we don't know the final amount. We don't know the initial amount, but we know that what we have is 0.69 of the original amount. So it had some original amount, don't know what it is. E to the negative ln t of 2. 2 and t are just too similar. You know what though? I don't even have my whiteout pen up here anymore. Oh, no. What to do? All right, I'm just gonna have to force it into a 2. All right, negative ln 2 over 5770. And we know that the final amount at this point in time, whatever point in time that is, trying to solve for that, is 0.69 of the original. So instead of saying it was half the original like we did for half-life, remember we did something similar for half-life. We said, okay, well, you know, it's half the amount at 5770. We're going to do something similar in this case and say 69% of the original amount. Don't use a percentage though. Remember that we in math don't use percents in our functions unless we're specifically told that a value represents a percent. We need to use the decimal. Otherwise, you'd be saying like it's 69 times the original amount, which is not what you mean to say. All right, but now you can go ahead and cancel out these q sub naughts on both sides. Divide them out. And then you get 0.69 is e to the negative ln2 over 5770 t. And now we just need to solve for t, but we already know how to do that. So let's go ahead and take the natural log on both sides. When we take the natural log on the right, you get negative ln2 over 5770 t. And then to get t by itself, we'll divide both sides by this quantity. If you'd like, instead of dividing by negative ln2 over 5770, you can multiply by the reciprocal. So that's probably what I'm going to do. I'm just going to multiply both sides by 5770 over negative ln2. Whatever you do, please don't try to cancel out these natural logs. It doesn't work like that. You're just going to have to hang on to them both. All right, back to this. So now we can say that t is, now these two are going to cancel, and that's going to leave you with 5770 ln 0.69 divided by negative ln2. That is the exact value, but we're going to make it look a little bit nicer. So let's do that. Nothing wrong with making it look nicer at the end. So when I ask you to round, I'm only going to ask you to round at the end of the problem. Until that point, keep everything exact. Don't approximate your natural logs until you're done. 5770 times the natural log of 0.69 divided by, and I'm going to put parentheses around this because it's negative natural log 2 parentheses. And you should be getting, and make sure this makes sense, 3088-ish, 3089-ish years. I mean, it's a skull, so I would think that would make sense. I mean, I guess technically you could say like it's been 3 years. Personally, I know nothing about how quickly bodies decay, so it's a little bit hard for me to answer this one. And I mean, a skull can be almost anything, years old. All right, so t is going to be approximately 3088, I don't know, 0.9 years old. You could have just said 3089, but all right, the last thing we're going to do is logistic growth. I don't know if we did this in your algebra class, maybe not. But this is what the function looks like. It's got an additional variable because we're not just talking about an initial amount, we're talking about a and b. And don't think you can just move this e to the negative kt up, make it positive, because remember, you've got another quantity here in the denominator. So it's not up itself, so you can't just move it around willy-nilly. All right, let's read the question. A small population of 6 deer are introduced to an island. Their population is modeled by a logistic curve, where k equals 0.32. After 10 years, there are 90 deer on the island. How many deer are there in t years? So the first thing we're being asked to do is just find the model that correlates to this data. Now, you have a picture over here of what a logistic curve looks like. So you see the population size over time, and how as time goes on, the population increases. and it starts to increase pretty rapidly, but then that increase will slow down. So it's still increasing, but it's doing so at a decreasing rate. And at some point, the rate of increase will slow down to zero as the growth slows down and kind of levels off, and the population's going to hit a ceiling, which I think helps. You can kind of see the floor and the ceiling here. So we'll look at the graph for this, but let's first talk about what our quantities might represent here. Now, I know the function's not the same. It's not Q of t equals Q sub naught e to the kt, but it's the same idea. We still have a Q of t and a t. Now, some of the important information that you're seeing here would be that 6 deer were introduced to an island. Okay, so at the beginning, 6 deer were put on the island. So that means that at time equals 0, at the beginning, there were 6 deer. So we can say that Q of 0 equals 6, or Q of t when t equals 0 is 6. But 6 deer are introduced. What that means is just we have Q of 0 equals 6. And their population is modeled by a logistic curve. We were already given our value for K here, which maybe you're thinking like, oh, perfect, we usually have to find K, and we were given K, awesome, we don't have to do anything. Well, that's not quite true. If after 10 years there are 90 deer, so 10 years, 90 deer means Q of 10 equals 90. How many deer are there in t years? So we need to find a model that represents this data. Now, notice that you're given values for Q and T 2 times, but you're not given any information about A and B. You know something about K, so you're going to have to set up 2 different functions here and then see if you can figure out what you need to do with it. Of course, I'll tell you, but you'd be thinking about this. Find the logistic growth model. Okay, so at 0, we know that Q of 0 is 6. So let's see. How do I want to write this? All right, so at t equals 0, we know that 6 is A over 1 plus B e to the negative 0.32, and then t is 0 in this case. The other function that you're going to have to write is based off of the other piece of information. So this is not your standard exponential growth and decay. Different situation here. The logistic model doesn't work the same way. I know that the population is going to be 90 when t equals 10. So 90 is going to be A over 1 plus B e to the negative 0.32 times 10. All right, so I've got 2 equations and 2 unknowns. When you had something like that happen back in algebra so long ago, you solved a system of equations. In order to solve an equation with 2 unknowns, you have to at least have 2 equations to do so. So what the plan is here is to first isolate A in both equations, and then we can use the value of A to solve for B. First, isolate A in each equation. Then solve for B. And then I'm going to say substitute I want to say substitute. Let's say, isolate A in each equation, then solve for B, and then substitute the value to find A in one of the equations. Okay. I know some of you, and some of you will think that this is fun. You haven't done this in a while, and others will be not so happy. I'm sorry. Okay, I've got 2 equations. I'm going to be doing the same thing each time. I might want to simplify these a little bit first, just because, for instance, e to the 0 power is 1. So that makes my life a little bit easier here. Negative 0.32 times 0 is 0, e to the 0 is 1. So I can rewrite this equation as a over 1 plus b. So that's easy for me. The other equation, I can't really do a whole lot with that, but I can at least just multiply by 10 to make this look a little bit better. So this will be b e to the negative, and then instead of 0.32, it'll be negative 3.2. Okay, so I'm going to do the same thing in each equation. I'm probably going to just work on them one at a time, but I'm trying to isolate a. If I want to do that, I need to just multiply both sides by the denominator. And then I'll get the denominators to cancel. Now I can say that in the first equation, a is equal to 6 plus 6b when I distribute. Okay, that's good. In the other equation, I can say that I'm going to multiply both sides again by the denominator. I don't have a lot of space to do this, but and I'm going to multiply it here, 1 plus e to the negative 3.2, and those will cancel. Now I have 90 times 1 plus b e to the negative 3.2 is equal to a. Oh, that's what I had to do. Okay. Whoops. All right, so now I'm saying a is this quantity, but a is also the quantity. So now I can solve for b by setting these two equal to each other. No matter what, if a has to be the same value in both of these, I'm going to go ahead and use that fact to isolate b. So this is the same thing that you did back in algebra when you were working on using substitution to solve a system of equations, except then you had y and x. You were like, okay, if y equals this expression in x and y equals that expression in x, let's set the two equal to each other. And that's what we're doing here. It just looks different because it's a and b in this case. All right, so we're going to take our 6 plus 6b and set it equal to the right-hand side. I'm going to go ahead and distribute. So 90 plus 90be to the negative 3.2. And then we're going to just solve for b. So in order to do that, we want to get all the b's on one side of the equation. So I'm going to subtract 6 from both sides, and then actually, I guess it doesn't matter which one you move where. I guess I'll subtract 6 though from both sides. All right, so I'm going to move the 6 over here, and then we'll bring the b's over to the left, the non-b's to the right. So I'm going to subtract 90 be to the negative 3.2 from both sides. And you don't have to write all that. I just want you to see what I'm doing. 90 minus 6 is 84. And then on the left-hand side, I have 6b minus 90b e to the negative 3.2. Now, if I want to solve for b, I want to factor out the b. So that's what I'm going to do next. I'm going to say that this is b times 6 minus 90 e to the negative 3.2 is 84. Now I've factored the b out of the left-hand side. To solve for b, I can just divide both sides by this factor. So now we can say b is 84 divided by 6 minus 90e to the negative 3.2. And we could simplify this a little bit. Like, for instance, I know that 84, 6, and 90 are all divisible by 2. So I could do that. So like 42 over 30 minus 45 e to the negative 3.2. 42 is divisible by 3 and 45 is divisible by 3. So I guess the GCF there was actually 6. Yeah, 84 divided by 6. Why did that not occur to me? That's fine. 42 divided by 3 is 14. Divided by 1 minus, and then 45 divided by 3 is 15e to the negative 3.2. Oh, I'm making this take up so much space. Sorry. Okay. And we're just going to have to approximate these, by the way. We're going to have to just get close. I know, so I did all this work for what? I'm also going to now find A. I'm going to back substitute using one of the original equations for A. So if I know B now, I can say that A is 6 plus 6B, which is 6 plus 6 times that quantity. And we'll just approximate both of these to put them in our function. I know I've made such a big deal about not approximating anything. But in this case, you're going to end up with a super messy function if you don't approximate in these logistic models. So approximate at the end, only at the end. But let's do that now. So first we'll find B. This is 14 divided by 1 minus 15 times e to the negative 3.2. And this is approximately, I mean, it's so close. You can just approximate it to 36. So we're going to use it in the function. And then for A, this is just going to be 6 plus 6 times that value. 6 plus 6 times the answer. And you'll get about 222. And you can leave that. I know. With the logistic model round at the end. Now let's write it out so that you have it, because it's technically what you were supposed to find here. I got to find a place to put it now. Okay, so this is what it looks like. Q of t is A over 1 plus B e to the negative kt. So let's put it all together now that we have A and B. So we'll say that Q of t, this is the model we're going to use, is A, which is 222, divided by 1 plus B is 36, times E to the negative K is 0.32, and then times T. Sorry, that's a little messy. We do the best we can. Okay. Now we're going to use this to answer a question on the next page, which is the last page of this one. So I'm going to rewrite this on the next page so we can see it. Refer back to it. Determine the population in 15 years. That's the population. Yeah, I'm going to rewrite this just so we have it. Because down the road, I'm not going to be able to see it. 222 divided by 1 plus 36 e to the negative 0.32 t. Determine the population in 15 years. Well, t is representing a quantity of time. So what we're looking for is q of 15. So that means we're going to take our function, and wherever we see t, we're going to substitute 15. Okay, so again, put this into your calculator and approximate this value. So 222 divided by, just be really careful with your parentheses here. As long as you have this written out on your test or quiz, and I can see that you knew what to do and you get a different decimal approximation, I'll know you entered it into your calculator wrong. And you'll still get credit though for putting the function together. Just, you won't get credit for finding the answer, but you'll still get partial credit. So make sure you're writing your functions. 222 divided by 1 plus 36 e to the negative 0.32 times 15. And then I will close that off with a parenthesis, and you should get about 171.26. Okay, so let's talk about that. This is a population, not of people, but of deer. 171.26. And remember, this is a rounded value, but it probably would have been rounded regardless. And I don't think it was rounded enough to, like, that it maybe would have been 172. But it's 171.26. Since we're talking about deer and you can't have 0.26 of a deer, then you could say that this is approximately 171 deer. Okay. Are you reading part C and you're like, ugh, how fast is the population changing in 15 years? That means find Q prime. But that's okay. We can do that. Come on. We did so much of this already in this class. This is nothing new. Let's buck up and do it. Find Q prime. I'm going to use the quotient rule. F prime is 0. So F prime G, doesn't matter what G is. I'm not going to bother rewriting it because it's going to 0 out anyway. Minus F times G prime. So the derivative in the denominator, well, the derivative of 1 is 0. For this expression, I'm going to keep the expression as is and then multiply by the derivative of the inside function. The inside function is negative 0.32t. Its derivative then is negative 0.32. So we have that divided by g squared. Now, again, I'm not asking you to find a derivative and simplify it. I mean, I guess if you find it easier to get your quantity by simplifying it, then do that. You're really just being asked to find how fast the population is changing in 15 years. So as long as you can take this quantity and sub in 15 for t, that's all you really have to do. I'm going to simplify mine a little bit just so, I don't know, looks a little bit better when I enter it into my calculator. But what if I simplify it wrong? So you do need to be a little bit careful about that. I'm just going to multiply the 222 by 0.32, at least just to get these two multiplied together, and then maybe multiply that by 36. Remember, a negative times a negative is a positive, so this gives us a positive quantity, at least in the numerator. Okay, so my new constant multiple is 2557.44. And then that would be e to the negative 0.32. And we're going to substitute 15 here for t, divided by 1 plus 36 e to the negative 0.32 times 15, quantity squared. Sorry, my writing is getting a little funky in this space. All right, so I've got this value. I'm going to pull that up, times e to the negative 0.32 times 15 divided by parenthesis 1 plus 36 e to the negative 0.32 times 15 squared. You see that? 12.53-ish. I get 12.53 deer per year. Since it's deer, if this is on WebAssign, they might give you instructions to like round up or round down to the nearest deer. I don't know. I'm just going to leave mine. Just don't forget that with your units, when you're talking about derivatives, you're not just saying deer. You're talking about a change in deer over time. So it's about 12.53 deer per year. And you know that is an increasing quantity. So the number of deer is going to continue to increase until it hits that ceiling. Graph the function and approximate the inflection point, then interpret the inflection point in practical terms. Okay, so this kind of takes us back to that general view of the graph that was given to us when the logistic function was introduced. So we're going to graph ours, and we're going to have to just be mindful of our population size when we look at the window for the information that we have. Let's see. Like for instance, I know that after 15 years, we have 171 deer. So if the x-axis is representing time and the y-axis is representing population, I'm going to have to make sure my y-axis is going up to some pretty high values. Let's see. Into the graphing calculator now. My function is q of t. I don't want to put in q of 15, that's just a value, but I want to put in my q of t function that depends on the variable with respect to time. So 222 divided by parenthesis 1 plus 36 e to the negative 0.32 t. Oh, it's x for us. That don't change it to t. Your calculator will be confused. Okay. Now, if you graph this in Zoom 6, I know we're always starting out in Zoom 6. That's a negative time. You don't care about that. All right, so the initial population of deer was 6. So we said that at time equals 0, there were 6 deer on the island, if you remember that. Now, we know this is just going to continue going up. So let's go to our window. I'm going to start with an x-min of 0. And I don't know how many years we need to include here, but I would say at least 20, because we already talked about what's happening at 15 years. And then for the y values, the y-min is 0. Really could technically be 6, but it's not really going to matter in this case. The values are going to be so small. And then, I mean, 171 is, I say go up to 250 even. See what happens. Graph. And I need more values on the x-axis. I can tell because there's a leveling out that's happening, but there's a little bit more that I want to see here. So I'm going to go back to my window. Maybe you can take this out to like 30, at least 25. Let's go to 30. I might not need that much. We'll see. Oh, all right. Pretty happy with that. All right, so the inflection point is something we're supposed to eyeball here. Don't worry, you're not being asked to find the second derivative. I know it would be so terrible, right? You have no idea how to do that. I'm just kidding. You have all the resources you need to find the second derivative and determine the inflection point, but we're not going to be doing that manually. We're just going to eyeball it. So the idea here is to approximate the inflection point by looking at the graph and interpreting the inflection point in practical terms of the problem. So the inflection point is when the concavity changes from concave up cup to concave down frown. I know we're so technical in this class. If you had to approximate it, we'd probably say it happens like right about here when you change from a cup to a frown. If you want to, you can, I like never use this feature. You can trace. I just hit the trace button. And then just sort of bring this down to about where you think the inflection point is. I mean, I would say it's like right around 12, x equals 12. So after about 12 years is when you would hit that that highest the fastest rate of change of the growth. And then after that, you will see that the rate of change of the growth starts to slow. So it's still growing, but the rate of change of the growth will slow down. So this is about where I would eyeball that. I would say that maybe it's like right about at 12. Oh, you know what? The Y value was about like 126. But we can always look in the table. Let's see, we went to the table and we said, well, what happens at 12? It's like 125.16. So we would say that this is approximately occurs at 1225-ish. The inflection point means that the growth rate starts to slow down. So we would say the growth rate hits a max and then slows down. So the population was increasing the fastest at this point. Last question. What is population in the long run? So if you're kind of like, well, how would we know? Like, doesn't that keep increasing forever and ever? I mean, can it? The island can only house so many deer. Notice that with this curve, you end up at some point hitting this horizontal asymptote. At some point, it can't grow any farther. The growth approaches zero. So you need to determine where that asymptote occurs. So let's see, where is the horizontal asymptote? Oh, we don't know. We're going to find it though. Actually, we're going to talk about this as it relates to the limit as t approaches infinity. So as time continues on and on and on, forever and ever and ever, we could also kind of look at this in our table of values also. We could think about what happens to the population as t approaches infinity. Now our function was way up here, 222 plus 136 over 2, I'm sorry, 222 over 1 plus 36e to the negative 0.32 t. All right, so as t approaches infinity, I know it's been so long since we've looked at limits, 1 plus 36e to the negative infinity. Remember what happens as e approaches negative infinity. If you don't remember, I'll remind you what your exponential function looks like. You know, it's just a general exponential function. But as x gets increasingly large, y gets increasingly large. But as x gets increasingly small, y heads off to zero. So the limit as x approaches negative infinity of e to the x equals 0. So we need to think about that as it relates to this problem. If this quantity is going to approach 0, then this whole term approaches 0. And if that whole term is going to approach 0, then we're just looking at 222 divided by 1 plus 0 equals 222 deer. So this will work for any of these logistic growth problems just because you've got the same setup in each case. So you're focusing on what's happening, what value that numerator is going to head to as the denominator is going to be approaching 1 plus 0. But yeah, the population in the long run is about, remember this is the value that you found for A, it's about 222 deer. It can't possibly house anymore. And you know, like I said, you could look at this in your table. I could go back into my table set I could start the table when x equals, let's see, we're trying to get x to become increasingly large. I mean, we started at like x equals 25 or 30 in our graph, and we really noticed that's where leveling out started to occur. We could have this changed by 1 year. We could even set it to be auto. You know, we usually have an ask. But when I go to my table, notice how these values for x are increasing still, but the value for y, it's not increasing the way that it was before. So like we said that when x was about 12, we hit the maximum value of 125, or that maximum rate of change. The maximum rate of change is rate of change, which was about 125 deer. And you can see the deer really start to still increase by quite a bit. But then you see this start to level out. Now you're 209, 212, 215, 217, 218, 219. And here, as x keeps getting larger and larger and larger, you're trying to approach 222, but you can't. I know I'm saying you can't quite get there. It's because you can't quite get there. If you hover over this value, you're going to see that these values keep going up and up and up and up, but they're never going to quite get to 222. Your calculator is just rounding them. It's saying, it's close enough, but really, it's never going to get there. So now we're talking about years later, 63 years after those 6 years were introduced, and you still haven't hit 222. Really interesting, huh? Fascinating. Okay, you might want to go back and put your calculator back into ask. Just so you don't forget for later. Okay, that's it. Enjoy going over these exponential functions as models. A wonderful rest of your day, and I'll see you next time.